let's take a look at graphing some transformations of functions. So this first example, we're given the graph of f of x equals x squared, and we're asked to draw g of x, which is x squared plus 2. So I notice that first this has addition or subtraction in the given expression, and so I know automatically that that's a translation or a shift of the graph. I just have to figure out, is this shifting vertically or is it shifting horizontally? Okay, because the plus 2 occurs on the outside of the toolkit function, I then know that this is a vertical translation. Okay, so you can think of this as g of x is equal to f of x plus 2, where 2 is k. And that means that I'm just going to shift all of the points of the graph up 2 spaces. And it helps if I already have some of these points memorized, and that way I can just move them. And so negative 2, 4 is on the graph of f of x, but now negative 2 comma 6 is on the graph of g of x. Just shift that up 2 spaces and do the same for each of these. If you just want to shift the vertex up, this point at the origin, and then you can follow the typical pattern of a quadratic from there and connect them, and we get a graph that looks something like this. Okay, number 2, we are given the graph of f of x, which is x cubed, and we're going to graph g of x, which is the quantity x minus 2 cubed. Okay, so I notice where that minus 2 is located, which is inside or next to the x, inside of the toolkit function, f of x. And so this is going to be a shift, a horizontal shift of the graph. And we compare this to x minus k, and we see that k is 2. So we're going to shift right 2 spaces. For horizontal translations, if you just want to think that the shift is going to be the opposite of the sign inside, so if this is a minus 2, we're going to shift plus 2 spaces. However, if it were a plus 2, we would shift left 2 spaces, minus 2. So I pick a few points on the graph, and I'm going to shift them right 2 spaces and connect. And the graph ends up looking something like this. In example 3, we're given the graph of f of x, which is the square root of x, and we're going to graph g of x, which is 2 times the square root of x. Notice where that factor is located on the outside of the toolkit function, and so not only is this a dilation, this is a vertical dilation by a factor of 2. So what that tells me is each of the y values is now going to be twice as large as it once was. Now, how do I do that graphically? I'm just going to go to the graph and think about these points, what the y values are, and multiply them by 2. But this point at the origin, the y value is 0, and if you multiply it by 2, you still get 0. So we're still going to have a point at the origin. This next point at 1, 1, the y value is 1, but if I multiply that by 2, I now get a y value of 2. And then let's do one more. This next point is located at 4, 2, but I multiply the y value by 2, and I get a new point at 4, 4. Connect the points, and the new graph looks something like this. Okay, example 4, if f of x is equal to the absolute value of x, we're going to graph g of x, which is equal to the absolute value of 1/2 x. Okay, notice where that 1/2 is located. It's inside of the toolkit function, and therefore this is a horizontal dilation. And not just any horizontal dilation, it's a horizontal dilation by the reciprocal of 1/2. So a horizontal dilation by a factor of 2. So we're going to take the points on the initial function and we're going to multiply the x values by 2. So a point at the origin, the x value is still going to be 0. However, a point initially at 1, 1, the x value is multiplied by 2, and now I get a point at 2, 1. The next point is at 2, 2, but now it'll be at 4, 2. And then if you have those points, you just reflect them over and you can find the points on the opposite side of the y-axis. And connect those points to get another V-shaped graph. For the next example, we're given f of x equals x squared, and we want to graph g of x, which is negative x squared. Okay, notice where the negative is located. At first I know it's a reflection. The negative on the outside of the toolkit function tells me that this is going to be a reflection across the x-axis. What that's saying is really the y values change signs. Okay, and if the y values change signs, that's a reflection across x. Okay, so a point at the origin is still going to stay there. The point at 1, 1 on the new function g of x is 1, negative 1. And then at negative 1, 1, we're now going to be at negative 1, negative 1. Okay, and then do the same for the other points. And the graph will look something like this. And in this last example, we have a few different transformations on the absolute value function. So we're going to write those out given our toolkit function of y is equal to the absolute value of x. We have a stretch of the graph with the 3. We also have a reflection with the negative. And lastly, we have a shift with this minus 1. Okay, so we just have to say what kind of shifts and dilation and reflection that exist. And so the first is a reflection across the x-axis. Okay, since the 3 is on the outside of the absolute value of x, this is a vertical dilation. And then also the minus 1 is on the outside of the absolute value. So that's going to be a vertical translation. Now the order that we perform these transformations matters just as it would if we're evaluating expressions, PEMDAS, or please excuse my dear Aunt Sally. The order of operations applies. So we're going to do the dilation and or reflection first, or both at the same time, and then we're going to move lastly. Okay, so vertical dilation. So I'll do them in that order. So first, if I just stretch the graph, the new function is going to look something like this. Okay, next I'm going to reflect it over the x-axis. Okay, and we get a function that looks like that. And lastly, a vertical translation of negative 1. So we're going to shift this graph down 1 space. And the final graph would look something like this.